So what I wanted to do is I want to talk about the next group of topics. It's on property of circuits. So in order to cover property of circuits, we need a few vocabulary words. I'm sure we're going to start off with. And ta-da! Those are the three vocabulary words we're going to be talking about. Voltage, resistance, and current. Okay? Now voltage we've already kind of experienced. When we talked about potential, we talked about this ability to have energy. Potential to have energy, if you will. Voltage is something similar to that. When you're dealing with electrostatics, imagine that you have a charge located some distance away, and that potential is going outwards. Now we have the equation of for electrostatics, K, Q, R for potential. So as we move further and further away, it falls off. So if I double my radius, this being 1R, this being 2R, this being 3R, my potential is reduced by a third at this point. Not a half, a third. Okay? So that was when we were talking about potential. Now voltage is really, really similar to that in the fact that voltage only talks about the difference between the potentials here. It talks about the difference there. Okay, so when we refer to the voltage of something, we're referring to the difference. So that's our definition of voltage. So the next group of things we want to talk about, the next big broad topic, is properties of circuits. So in order to talk about properties of circuits, we need circuits, not circus. We need to come up with a few vocabulary words to talk about. And here are the three that we're going to start with. We're going to talk about a few more later on, like capacitance, inductance, that sort of stuff. But as it stands right now, those are the three we need to really concentrate on. Voltage, resistance, and current. Now the first one, voltage, we've kind of already experienced, and that's why we're starting with that one. When we were talking about our modern forces, and mind you, they're not terribly modern, when we were talking about those modern forces, we came up with a term, and the term was potential. And remember that potential is the ability to have energy. One charge or one system or one planet, whatever, has the ability to have energy if you introduce another mass into the system. In the case of a planet. In the case of a charge, if I introduce another charge into the system, it gains energy. Voltage is along those same lines. Now, imagine we have a charge here, okay? And we can say that the potential due to that charge falls off like K, Q over R, okay? Seem to be hitting all of the little spots. Falls off like K, Q over R. Is that better? That's better. So at a given radius, it has a particular amount of potential energy. But if I double that radius, I have half that potential energy. If I continue to move up and triple that radius, this being R, this being 2R, this being 3R, I've cut my potential energy in third. Now, when we're referring to voltage, we're referring to the change in an object's potential. So, if we look at potential, or voltage, we're looking at how much that potential has changed over those points. Okay? So when we're referring to potential, or not potential, voltage, we're referring to how much that's changed. So from here to here, there's a change of 2R, basically, or it's you know, if we're referring from this point being our initial point and that point being our final point, we're referring to a change of potential of half. Half of my potential is gone. Going the other way, I've doubled my potential. So that's voltage. It's that change in potential. When we refer to voltage, we're referring to how much that potential changes. And why is it important to refer to it as a change in potential instead of potential? Well, when we're dealing with objects and we're dealing with motion and objects moving, it's the changes in energy states that move objects from one state to another. You talk about a rock on top of a mountain. Moving down that mountain, it enters a high potential energy zone and goes into a lower potential energy zone. reducing its potential energy. That's what motivates it. It's the change in it. It's not the exact values of those potentials. It's just the change in potentials that allows that object to be motivated. Okay, the next topic I want to talk about is resistance. So, what I like to say about resistance is I like to think of resistance as being along the lines of Newton's second law. When we looked at Newton's second law, we said F is equal to ma, right? And remember, that's not quite right. It's the summation of my forces is equal to mass times acceleration. When I think of resistance, I think of it very similar to that. I think of resistance as this property that resists the motion of charge in a system. So when you look at a circuit, the circuit has a given amount of resistance. And you can think of that as kind of like an inertia. It's not quite the same thing. But you can think of it as an inertia, as a resistance to the motion. So as charges are trying to move from one point of that circuit to another, it's the resistance in here that slows or actually reduces the amount of charge that's allowed to move from one point to another. Okay? So that's resistance. It's basically a resistance to the motion of charge. It slows down the amount of charge that's allowed to get from one point to another. Okay? So that's resistance. And the last thing is current. Now current is charge. So when we talk about current, we're talking about the motion of charge. Okay? And we don't think of it as a velocity, even though it's something similar to that. When you look at a piece of wire, and I'm using a big cross-sectional area here. Okay? When you look at a piece of wire, current is the measurement of charge that travels through a cross-sectional area. So through this piece of wire, how many coulombs are traveling through that piece of wire? That's current. Now current is referred to as an ampere, or simply put as an amp, which is a base unit. Strangely enough, an amp ends up being a base unit, but we can refer to an amp as a charge per second or coulombs per second, or I guess it'd be charge per time, coulombs per second. So when we're referring to an amp, you can think of it as a coulomb per second or charge per given amount of time. Okay? That is an amp. That's current. Now when we talk about resistance, resistance is an ohm, which is expressed by an omega. Okay? That's an ohm. So when you see 30 ohms, 40 ohms, 10 ohms, you're measuring the amount of resistance that is experienced there. Okay? And we'll actually go in and talk about Ohm's law real quickly. And then lastly, voltage is voltage. It's the change in potential, which would make it a joule per coulomb. Okay? Typically expressed as a V. Okay? Cool? Now, or delta V actually. Now, in a mathematical equation, voltage is V. Now, to separate it from velocity, we don't put anything over it, we just leave it as a V. Resistance, fortunately enough, is an R. Okay? And then current, because coulombs are already being used for K, R for C, current is an I. Okay, so whenever you see those kind of notations in the equation, wow, I hit that one dead center here. Let me just block it out. I. Okay? It's I. Cool? So, voltage, current, or voltage, resistance, current. Voltage is a V, resistance is an R, current is an I. Current is also the base unit. An amp is a base unit. Now, resistance is not a base unit. When we talk about Ohm's law, we can derive the units for resistance. And voltage is certainly not a base unit. It's joules per coulomb, typically. Okay, cool. So that is the vocabulary that we need to do to talk about properties of circuits.